celebrate the gravitational waves. Hey! I think it's the greatest discovery of this century, probably. So anyway, so before we celebrate and get drunk, let's discuss a little bit of inflation. So inflation is not standard physics. It's something which is postulated and, that hopefully can be verified in some future. But what it is like a postulated era before the radiation-dominated universe started. And it's characterized by the fact that the co-moving Hubble radius, which is defined over here, is decreasing like crazy in almost an instant. So that's why you can define how much this radius has decreased from an initial radius to the final radius. And this is supposed to be like exponential, so it's a huge number. And this huge number is parameterized by this power n, and that's called number of e-folds. Okay, so if you want, you can imagine a picture like this. So if our universe were closed and we are sitting, well, somewhere here, then let's say the initial, so the physical meaning of this co-moving Hubble radius is really, it's a co-moving distance where particles can sort of communicate at that time. So the co-moving distance from us at the beginning of inflation was Ri hat, and then in an instant it basically shrank to R star hat. And then it started re-expanding again in the radiation and matter-dominated eras. And so now, today, it's actually somewhere here. So in order the inflation to be efficient in addressing the puzzles, which I'll discuss today, you really need that this R0 today is at least smaller than the initial one, right? Otherwise, you cannot describe these puzzles. But usually, people assume that this is still much, much bigger than R0 hat. And so in some sense, you may say, well, at this point, we see a star here, and we see a star here, are puzzling, and we are puzzling why they have the same physics. But of course, they were in contact because they are in this big region which was in contact in the past, right? So there was plenty of time to communicate physics between these two distant regions, and then of course, these would be completely disconnected. So if I have a star here and star here, they will be completely disconnected at the end of inflation, when the radiation-dominated era starts. And they are still sort of disconnected now, but they were in contact in the past. And so that's basically the idea of inflation. Inflation ended. Nobody knows how. But that end of inflation is sort of called reheating. So what you need to do is that, well, this is sort of like a cold universe. So somehow the inflation is driven by something, and that something in the end has to give energy to particles of standard model. And so after the inflation ended, sort of, your hot Big Bang starts, and this is called reheating. So that energy of the inflaton of whatever that drove the inflation, turned and transferred to the standard model particles. And so now they have all this kinetic energy. They are really, really hot. They are all relativistic. And that's how the Big Bang started. So reheating and then hot Big Bang started, as we know it. Okay, but the physics of reheating, or how this energy transfer goes, from it's unclear. And so this is only a framework. It's not one theory. It's a framework for many possible theories. Okay, so now let me discuss three puzzles. And we sort of already know all of them. So the first one is very familiar to us, horizon problem. Horizon. And so basically, the standard cosmology doesn't explain why we see homogeneous universe if you look there and you look there, because at the time of recombination, these were definitely disconnected pieces of the universe. So why we see homogeneous universe? And we have already constructed a solution in your tutorial, so just let me remind that. So if you have really, so that's this picture here. So if you have decelerating universe in the radiation and matter-dominated eras, then, and you are somewhere here, at this point, this is your past light cone. This is the time of recombination when the CMB was released. This is the time of Big Bang, but of course this guy has this past, this guy has this past. There is no overlap in between them, so why the physics here and there is correlated. And what inflation gives you is that this era was preceded by the era where A double dot was actually bigger than 0. And what it does, it buys you more conformal time. Okay, so now the picture looks like this. Again, the same picture as we had before. But now eta doesn't end at equal to 0, but it can go to negative values. So that's why, if this is my eta CMB, then there's an overlap over here. So there's plenty of time when this guy and that guy could communicate in the past. So that's a solution offered by inflation. And in order this to work, so you need something like these 40 to 60 e-folds, so that so that there is plenty of time to communicate. Otherwise, it's like 10 to the 4 disconnected pieces at the time when CMB was released. So you have to connect all of them, and that's why that gives you how much conformal time I have to put in here in order these regions to communicate. And so, in some sense, this means that inflation. Let's put a motto: inflation drives universe to homogeneity and anisotropy. Okay, so that's a motto of this thing, but it's explained over here. Okay, so the second problem, this is the first problem. The second problem is the flatness problem, which is not, well, it's not that nice problem as the horizon problem, but it's also a problem. Flatness problem. And so if you think about how the energy density of various matter components behave in various eras, so for example, you know that rho of radiation goes like a to the 4, and then rho of matter goes like a cube, and rho of the curvature, if you want to define it, goes like 1 over a square, and then rho of lambda, if we have lambda, goes like a to the 0. So then I put them in these decreasing powers. So you would expect that this guy, when A is small, is dominant. So the radiation is dominated first, and then the matter dominates. And then there should be an era where actually the curvature dominates, right? And then there should be era where lambda dominates in some sense, because of just this power structure, right? But the problem is that we have never seen this era. So why, the question is, why curvature not come to dominate yet? Right? Because it's just studying these powers. If whatever stands here is non-trivial, then there should be a curvature-dominated era following the matter-dominated era, but we haven't seen that. So in other words, this rho k must be really very small for some reason. And that's because we are basically living close to the flat universe. So let me just reformulate it in a slightly different terms. So if you write down your Friedman equation, and I just separate. Why didn't I get a 3? Doesn't matter. So, and then I separate whatever the other contributions are in this row, and then I separate the curvature out. So this is my Friedman equation. And then you remember that the critical density is just defined as if k were equal to 0. So it's just 3 m Planck square h square. Okay. So now if I, let's say, write instead of h square this row critical 3m Planck square and divide the 2, then you get an equation that rho over rho critical equals to 1 plus k 1 over h square h square. Okay, so just divide everything by h square. I get 1 here, I get whatever the rho critical here, and I get this thing here. So now if you look at this, this is nothing else than 1 plus k r hat square. Okay, so that's our favorite commutative Hubble radius there. So now what is observed now? So today, the observation gives you that rho over rho critical now is something like 1 plus 0.01. Okay, so now it means, but we live in the era where this is true. So whenever the universe is decelerating, actually r hat is growing. So now if I track this equation to the past, so this is what we observe now, and sort of r hat is something, right? But in the past, r hat had to be much smaller. Okay, much smaller, because in this era where I have matter domination and radiation domination, r hat is increasing. Okay, so you can sort of estimate how rho over rho critical was in the past, for example, at the time of BBN. Okay, and if you find that, well, this is much smaller, so it's 1 plus something which is much smaller than 0.01, and the reasonable estimate is something like 10 to minus 31. So why the hell, at the time of BBN, you had so fine-tuned contribution to so fine-tuned density of the universe, right? So this is now. This had to be in the past because R was growing all the time from BBN. It is expanded a lot. So this is really extremely fine-tuned. Fine-tuning. Okay. So now you may ask, when I created the universe, when the Big Bang actually started, right? So, or slightly after the Big Bang, why I'm so close to 1? And the answer inflation, offers to you is that if you look at that picture over there, we know that R0 hat today is there, but actually when the universe started, Ri was much bigger than R0 hat. So in fact, when you created the universe, this fine-tuning didn't have to happen because R hat was much bigger. So this could have been significantly different. Right? It's only after the inflation happened, this is so fine-tuned. So actually, inflation does for you the fine-tuning. Okay. So if you want, so inflation offers an idea that K-dominated era might yet to come. Right, from the picture. So see the picture there. Right? Does it make sense?
No.
Why not?
I don't know.
Okay, so look at this equation. Look at this equation.
Yeah.
Okay, so now if I take, so now you know that this is something like this. Okay, so in the past, if we had only radiation, because as you are going to the past, R hat is decreasing. So for example, we are at R star before the radiation era. So this was much, much smaller. That means that rho over rho critical is basically 1 to much better precision in the past, right? So that makes sense. So now, if that were true, then we would have to assume very, very fine tuning. But inflation is different. So he says, okay, but at the beginning, it's actually Ri hat, not R star hat, which happened. That means that Ri hat is much, much bigger than R star hat. So actually, these could have been significantly different from each other in the past. So that's the idea, basically. And in some sense, because, well, now we have lambda dominated era, but if we didn't, then our R0 hat is, is increasing all the time. So maybe, after many, many billion years, we come to this Ri hat initial, and then we'll find that this ratio is 1.5 or something like that. That's possible, right?
So then how does that mean we would be in the equation?
Yeah, that would mean that.
How? Why?
Well, because the matter, well, if there were no lambda, of course. So the matter disappears, the radiation disappears because it goes like 1 over a to the 4, this goes like 1 over a cubed. So this one has to dominate. Right? Of course, now, because we have lambda, it's slightly different, right?
Do you have to fine-tune inflationary models so that it actually produces rho over rho critical pretty close to 1? Like, is it just pushing the fine-tuning further away? Or?
Yeah, exactly. Well,
it's
telling you that at the beginning you didn't have to have it. But in order to have this fine-tuning as we see it now, so in order to explain this guy here, yeah, you need number of e-folds. You need to decrease your...
So you need to fine-tune the inflationary model. Not
fine-tune. You need n between 40 and 60 or something like that. So you really have to prescribe, at least, I have to decrease my R hat that many times. Yeah. Okay, think of all this. So the final problem, the third problem, which is not really a problem if you don't believe in ground unified theories. But if you do believe in them, so it's called monopole problem. And basically, the idea is that, long time, in the past, you had basically temperatures so high that all the theories were, described by, let's say, some ground unified theories. All the forces were the same, and then the symmetry breaking happened, and then we have the standard model emerging from there, where we don't see any more these symmetries. Okay, so at that time of the symmetry breaking, so got symmetry breaking, which happens at T-cut, which is something like 10 to the 16 GeV, for example. So as you break the symmetry, you basically break the vacuum if you want. So then you create a topological defect. And this is called monopole. And you create one monopole per one vacuum, which is per basically the conmoving Hubble volume. So per one horizon volume. Okay, so you would create lots of monopoles if this guy were really, really small, then you would create one monopole per this one tiny region, right? So now, later on, so you would see lots of monopoles, basically. But you don't see any monopoles. So that's why, actually, there's no monopole problem. So let me estimate this thing. So, sorry?
What are these monopoles?
Magnetic monopoles. Magnetic monopoles. Yeah. Okay. So let me estimate the physical distance between the monopoles when you created them. So when produced, so the produced, and in some sense, it's your co-moving distance times the scale at the time. So it's r hat times a, which is 1 over h at the time. Okay, so this is the physical distance, which is like the co-moving distance times the scale factor at the time. And the co-moving distance is really, how big at the time the particles could communicate, how big the horizon was at the time. Okay, so this is the produced. Now, let's assume that we have, there were no inflation, and we had radiation era all the way to the Big Bang. Okay, so if radiation era then you can use your favorite Friedman equation to estimate how big h was at the time. So you have h squared equals to rho over m Planck squared, but rho in the radiation era goes like t to the 4, right, at the time. Okay, so this goes like t to the 4 m Planck squared. Okay, so that's my estimate for h. So now I can plug it there, and then you see that distance between the monopoles when they were produced is something like it's 1 over h, so it's m Planck over t squared, and of course, the symmetry breaking happened at that temperature, so t gut square. Okay, so that's an estimate. How far the monopoles were from each other. What is the physical distance in between them? So of course now, the now is just the redshifted one. So it's t gut over t cmb times d then, so the produced. Okay, so now you can plug the numbers. So this guy, you can put whatever the t gut, this thing here is, and you find that this is something like 10 to the 4 kilometers. So you would expect, if you had radiation-dominated era all the time, you would expect that every 10 to the 4 kilometers, you would find a magnetic monopole. Okay, so now what would be the monopole density? So monopole energy density if you did find every 10 to the 4 kilometers, so would be rho monopole, which is the mass of the monopole, which you can estimate approximately at this gut scale, m gut, over d cube now. It's mass over volume. So now this thing is something like t gut over d cube now. And if you plug in this d now and t gut again, t to the 16 GeV, then you find that this is something like 10 to the 17 rho critical. Okay, so you have really huge density stored in these monopoles. It's simply because these monopoles are so heavy, they have so much energy in them that if you find a monopole every 10 to the 4 kilometers, then you know the universe would collapse, and you know, okay. So that means that, well, monopoles so heavy that universe would collapse long time ago. You just couldn't bear it, right? It would collapse long time ago. Okay. So this is the calculation if we had radiation all the time. But of course, if the inflation is here, then if you look at this D when they were produced, it depends on this H when they were produced, or if you want, it depends on this R hat. Again, if inflation is true, then R hat at the beginning of inflation was much, much bigger. So basically, you find the monopoles which are much, much diluted now, right? So inflation dilutes monopoles. And by this exponential factor given by your n. So that's a solution to this monopole problem. That's why we don't see monopoles in the universe around ourselves, because inflation diluted them and we just see them, you know, much scarcer. We don't see them. Anyway. Okay, so of course, this is only if you believe in guts, but people, when they formulated inflation, actually there was the time for gut theories, right? So this was a serious argument. So now I'm still giving you this number n goes to 40, goes from 40 to 60. You can calculate it for each of these problems, and I'm not going to do it, but you will do it in your tutorial on Tuesday. So I just picked one of them. So this is sort of obvious. So I just picked the flatness problem, and you will calculate how much n you need in order to solve this flatness puzzle on Tuesday. Okay. So look forward to it. But basically, all the calculations are similar. So they are similar problems, so similar solutions. So but yeah, look forward to see how this n 40 to 60 comes out. Questions? Yes.
General feature of all guts that you create manifolds?
There's no way I have no idea. I'm not I don't know.
Okay.
But I would say, yeah, well, whenever.
Or is it just a very specific?
Whenever you have, like, phase transitions from one vacuum to another vacuum, you may create these topological defects. You don't have to create necessarily monopoles. You can create cosmic strings. You can create domain walls or whatever.
And you would run into the same kind of problems.
All right. So this is the framework, and then the framework solves these puzzles. And we haven't used any theory. We're just saying, well, it's expanding like crazy. So let's put this in numbers a little bit. So 2 conditions for inflation to happen. So one of them is rapidly shrinking Hubble sphere. So we had that dr hat over dt. So what it is equal to, so this is d over dt 1 over ah. And now it's an exercise on differentiating things. So I claim this is this thing, h dot, and then a square, h square. Well, that looks reasonable, probably true. So now I pull out 1 over a. And the first term just gives me 1. Because I'm using that a dot over a is h. And the other term gives me epsilon, where this epsilon is defined to be minus h dot over h squared. Okay. So now, if you want this guy to be much smaller than 0, so that your Hubble radius is really shrinking very, very fast. Okay, so if you look at this guy, okay, so this guy is already small, A is already small, but you know, you may, so you definitely require, if this were just smaller than 0, then you would require that epsilon is, well, from 0 to 1 or something like that. But if I want much, much smaller, well, you better want epsilon to be small so that you make this really, really big. So usually people state, so what is usually, so this is enough that this is smaller than 1, but usually people overdo it and put much, much smaller than 1. Okay, so then this is small, and I maximize that guy here. So that's one condition. So this is epsilon parameter, which is h dot over h squared, is much smaller than 1. Another condition is that the inflation has to last sufficiently long. To explain our puzzles. So you really need n going from 40 or 60 or something like that to solve puzzles, to resolve problems. Okay. So that means that, okay, I'll just write it, is another parameter eta, which is epsilon dot over h epsilon, and this is required to be much more than 1 in the absolute value. So, you know, it's not sufficient that epsilon is very small, but per each Hubble time, so this is 1 over h is Hubble time, so per Hubble time, epsilon cannot change significantly. So the ratio of epsilon dot over epsilon per Hubble time must be much more than 1. Because otherwise, you know, it wouldn't help me that I started epsilon much smaller than 1. If it, you know, starts changing drastically with time, then this condition won't be satisfied after some time, right? So I really need that the increments of epsilon in time are really, really small. Okay, so this is what this condition exactly means. Okay, makes sense, right? So that's the two conditions for the inflation to happen and for the inflation to last sufficiently long. Okay. So that's just the kinematics of the inflation, if you want. So now the second thing is, what kind of matter drives inflation? What is the content of the universe when it is inflating? So that's the physics part. So what kind of fluid drives inflation? And again, so let me start with these Friedmann equations. I have rho over 3 m Planck square. Now I'm putting all rho here. And then the other one is rho dot is minus 3h rho plus p. So now if you differentiate the first equation, so take, differentiate this one, then you get 2h dot. So finally, I'm actually deriving the Einstein equation here. So I was claiming that the Einstein equations are these two equations. in fact, this one is already integrated one. It's the first integral of the Einstein equation. So now I'll rederive by differentiating it once. I derive the Einstein equation, the true Einstein equation. Okay, so 2h h dot, and now it's just rho dot over 3 m Planck square. So for rho dot, I just plug this guy here. So this is equal to minus 3h rho plus p divided by 3 m Planck square. That comes from that equation here. On the other hand, what is this 2h h dot? So it's 2h, and now h dot is, well, h is a dot over a, and I have to differentiate it once. So what this guy is a dot over a dot, right? So it will produce a double dot. So a double dot over a, and then it will differentiate this guy, and it will have a dot square over a square. So it's minus h square. Okay, just differentiating h. But for h square, I again use the first equation. Okay, so this is equal to 2h a double dot over a minus rho over 3 m Planck square. Okay, just, you know, playing with equations, right? Your favorite hobby. Okay, so now I look at this part, and I look at that part, which are, of course, equal. So now you see that h gets cancelled here, and I will have an equation for a double dot in terms of rho and p. Okay, so then if you write it down, this is called acceleration equation, and that's actually the true Einstein equation. So a double dot over a equals to, and now if you put all the terms together, 6 m Planck square rho plus 3p. This is the acceleration equation. Okay. And of course, because it follows from the other two equations, it's equivalent to these equations if you want. Okay. So now, in order to have inflation, which means a double dot is actually bigger than 0, so inflation which is a double dot is bigger than 0. Well, if this were bigger than 0, that means that, well, this is negative, a is positive, so this guy has to be negative, right? So that means that rho plus 3p is actually smaller than 0. Or, if you want, w parameter is smaller than 1 over 3. Okay, so that's the condition for the inflation to happen. I need acceleration to be bigger than 0. Well, a double dot bigger than 0. Okay, so now this is an equation of state for my matter, which tries the, well, which dominates the universe at the time of inflation, if you want. So now the only problem with this thing is that it violates strong energy conditions in general relativity. So violates strong energy condition So in GR, if you know, either you don't know the equation of state exactly, or you just, you know, want to discuss the matter in general, you impose various energy conditions. So most of them, which is like the basic requirements on T mu you can ever have. So for example, that observer sees around himself only a positive energy density, for example, or that matter cannot move faster than the speed of light, or something like that. So these are various energy conditions. So one of them, strong energy condition, is actually violated by the matter which had to be present at inflation. What it tells you is that sort of classical regime of Einstein theory breaks down. Okay, so the classical GR at the time of inflation is not a reliable tool, although people use it anyway. Right. Well, this can be after Big Bang, right? But yeah, you're right.
Yeah, but I mean, we didn't have singularity without the inflation.
Well, they're fast on singularity. Yeah. Yeah. So anyway, so you violate this energy condition. So what? So this is the fluid which we need to construct, and the question is how we construct such fluid. And let me do it over there. I have to make it. So the physics of inflation. So let me first give you a very brief overview. Of few possibilities people came up with. So you are asking me, what kind of theory gives me that equation of state, and predicts this and satisfies those conditions which we impose on inflation to exist. And so a few examples. So one of them is false vacuum inflation. So basically, you are saying that that the universe is dominated by the constant density of metastable false vacuum. Okay, so usually, you are just sitting in that metastable false vacuum somewhere, like here, and sitting there, you just see constant energy density, and because you have something like lambda predicted by this thing, you have de Sitter expansion. Okay, so this leads to de Sitter expansion. So de Sitter expansion has, if you have de Sitter spacetime, then it's characterized by these two epsilon and eta parameters are exactly equal to 0, and h equals to a constant. So Hubble parameter is not changing during the de Sitter expansion, and everything is sort of exponentially. So A is proportional to E to HT. Okay, so your scale of the universe is exponentially expanding. Epsilon, so conditions are satisfied, and H is approximately equal to constant. Okay, so now what is the problem with this type of inflation is that, well, classically, you can never tunnel through this guy, let's say to that guy with small lambda. And so once you are in a minimum, classically you stay in that minimum. There's no way you can climb up the hill suddenly, right? So classically this inflation never ends. So that's a big problem. So we know that inflation had to end in order to see our universe, right? Because otherwise we wouldn't be here. So classically, this inflation never ends. So That's a problem. Quantum mechanically, of course, it can tunnel from one vacuum to another vacuum. But you know from Ruth's course that there is this, whatever, you have to put some stress energy in between the, well, you have like these expanding bubbles separating various vacua, right? And they carry some energy density, these bubbles. And so if you actually have created, let's say, a small bubble of a different vacuum here, this bubble is unstable, starts expanding, but on the way, it destroys everything it sees. So actually, so quantum mechanically, it ends. Quantum mechanically, it can end. It ends through tunneling. But the resulting universe is actually very, very different from what we see. But resulting universe different from what we see. Okay, so it's a possibility, but it's not entirely satisfactory. Well, holy grail of inflation is a single field slow roll inflation. Single field slow roll inflation. So that's something you say, well, the fluid I have to really produce, satisfy this energy condition and gives, satisfying these epsilon and eta conditions is just a single scalar field, basically. And that scalar field is called inflaton. So it's a scalar field, scalar phi, and that's called inflaton. And I'll study it in a minute, so let me postpone the study of this thing, because this is like really the simplest possible way to get inflation just with one scalar field. Okay, so another possibility, which is called hybrid inflation. So basically the next possibility is that you start putting more and more fields. So for example, hybrid inflation, the simplest way is you have two fields. So one of them, it's basically like the Higgs boson. So it's just, gives mass to the other inflation, to the other field. And once the original field, which is driving the inflation, becomes massive, inflation ends. Okay, so one field drives inflation. And the other one, second field, ends it, let's say through Higgs mechanism. Okay, you will discuss this in your explorations in cosmology, and you will also discuss a possibility of something which is called K-inflation, which is a weird possibility, is that you say, again, I have a scalar field, but that scalar field doesn't have a standard kinetic term, but it can have some weird kinetic terms, for example, a la Born-Infeld electrodynamics or something like that. So you can, usually these theories are not well defined, but somehow you can make them well defined. So you can play with, strange Lagrangians and see if they give you something interesting. And that will be discussed in exploration in cosmology as well. So now let me return back to this single field slow roll inflation, which is like the holy grail of inflation. Okay, so questions? Questions? Okay. So single field. And today I'll just probably write down a few equations, and then we'll study them probably tomorrow a little bit more. So you just postulate the simplest possible scalar field with some potential. So your action is an integral d4 of x square root of g r over 16 pi g Newton. And then you put the scalar field minus 1/2 g mu nu d mu phi d mu phi, and then minus the potential. Okay, so that's the scalar field. So if you write down the equations of motion, so you vary delta phi, then the equation of motion is boson phi minus v prime of phi equals to 0, which is your generalized Klein-Gordon equation if you want. So if I just take m square phi square potential here, I'll just get exactly the Klein-Gordon equation. Now, if you vary with respect to g mu nu, you get Einstein equations. But what is more interesting is the t mu nu, which you get from this thing here. So t mu nu, which is minus 2 over square root of g delta of the Lagrangian density delta g mu nu, just to remind you. And it's given by d mu phi minus 1/2 g mu nu d phi square minus g mu nu times v of phi. Okay, so if you plug it in, whatever is here, I just have to differentiate it with respect to the metric, and this is what you get. So now, interestingly, so this looks like strange t mu nu, but this is only a special case, if you want, of a t mu nu of a perfect fluid. So can identify with perfect fluid So let me just remind you, this is how perfect fluid is rho plus p u mu u nu plus p g mu nu. So this is t mu of a perfect fluid, if you want. And now we want to compare that guy with this guy. So, whatever stands in front of g mu nu must be related to my p. So this guy and that guy is related to p. And this thing must be related to u mu u nu, however times rho plus p. Okay? So from here, you can read that rho is minus 1/2 d phi square plus v. P is minus 1/2 d phi square minus v, and u mu is d mu phi, and I want to normalize it to minus d phi square. Okay, so if you do this identification, you just rewrite this guy in terms of that guy. Okay, but this has very interesting result. So now if I create this ratio p over rho, right? So it's this thing over that thing, minus 1/2 d phi square minus v over minus 1/2 d phi square plus v. Okay, so that's my equation of state, if you want. So immediately you see that if this guy and that guy are much smaller than V, so if this guy dominates and that guy dominates, then you get minus and plus. So you get -1 actually out of that, the equation of state, which certainly satisfy our requirement for inflation. So scalar field actually can be a source of inflation. So let me just write it down. So if you want, you have two regimes of interest for cosmology coming from the scalar field. And these are so let me call first one Bigly field. Which means that this guy is much bigger than V. Well, if that guy is much bigger than V, I can neglect V in that equation of state. I get something over something. So W is equal to 1. Now, recalling that your solution of your continuity equation is A minus 3, 1 plus W. So if W is equal to 1, then A, so rho goes as A to -6. Okay. So rho goes like 1 over A to the 6. And this is the right regime to describe inhomogeneities. You'll probably not do that, but you will do it in your explorations. Okay. The other limit is when exactly the opposite is true. So that's a smooth field. So now d phi square is much smaller than V. In which case we have W equal to -1. And if W is equal to -1, I have rho equal to constant. Rho equals to A to some power A0, which is precisely, if you want, the lambda, well, so can do for inflation. Certainly satisfies the condition I derived. It must be satisfied for inflation. So scalar field can do the job, provided this is true. Okay, so I have to design a potential, such a potential for the scalar field, so that I satisfy this equation, if you want. Of course, this is only satisfying for that, you know, violating the strong energy condition. I still need to satisfy the conditions for epsilon and conditions for eta in order my inflation lasts so long and it's actually doing the job I need it to do. Okay, so maybe it's, well, okay. So the last thing I will write down is that we will return, so far here phi is a function of x and t, if you want. So this is completely general. But for cosmology, let's take FRW space as a background in some sense. And then you know that the matter only which is consistent with homogeneity and isotropy actually can, you know, is reasonable matter to consider. So consistency, and I'll start from here tomorrow, consistency with symmetries of FRW. It tells me that phi cannot depend on x, because if it did, it would vary from place to place, and I wouldn't have homogeneity, right? So it tells you that phi is a function of time only. So now, if phi is a function of time only, let me look at, for example, well, So I know what energy density is this guy here, but the spatial derivatives disappear. So only time derivative in rho persists. So then I have my Friedmann equation, which is 3 m Planck square h square equals to the energy density, and the energy density is over there, but now only with time derivatives, and then plus v here. Okay, so spatial derivatives are gone. And this equation over here, so you have box on phi, and again, you neglect the spatial derivatives, and you have basically 2-time derivatives. So the Klein-Gordon equation gives you, if you plug it in, phi dot plus v prime of phi equals to 0. And these are the two equations which govern your scalar field and which backreact your scalar field on the geometry. So I'll start from here tomorrow. Questions?